Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration. Hi there, welcome to the 8th episode of Cyclopod. Today, we make an excursion into the North Sea, to the border area between the exclusive economic zones of the UK and Norway. So that's where we are going in space. In geologic time, we're going back 56 million years to the Paleocene-Eocene thermal maximum, in short, the PETM. For those of you who are new to the field of paleoclimatology, the PETM is a geologic time interval that has been studied in very much detail. And that is because it is often considered a useful analog for the ongoing man-made perturbation of the global carbon cycle. Just as today, the PETM is characterized by a rapid release of carbon and greenhouse gases into the atmosphere, leading to a very fast warming of about 5 degrees C 56 million years ago. Our guest today is Simin Jin. She is a PhD student from the China University of Geosciences in Wuhan. And about a year ago, I've seen her conference talk at the General Assembly of the European Geosciences Union. That talk was so impressive that I wrote down her name on a little post-it to remind me to watch out for her final peer-reviewed paper to come out. And that day came on December 9th, 2021. That's when Simin's paper appeared in EPSL, Earth and Planetary Science Letters, with the title Large-Scale Astronomical Paste Sediment Input to the North Sea Basin during the Paleocene-Eocene Thermal Maximum. Simin, very welcome to Cyclopod, and congratulations on the publication of your paper. Is this your first author paper?
Hi, David. Thank you very much for inviting me to your Cyclopod. Yes, it is my first author paper.
Oh, wow. Very well done. Your paper describes a PTM interval in a siliciclastic environment, very different to the classic PTM sequences in the pelagic or the hemipelagic settings that I am more familiar with in IODP sediment cores. But you worked on sediment cores from a borehole drilled by Shell, correct? Can you describe the lithologies that you observed?
Yeah, these samples come from a well in the North Sea basin drilled by Shell. The negative carbon isotope excursion marking the PTM in this succession spans as long as 140.2 meters and is coeval with the occurrence of more than 200 turbidite sandstone beds in an otherwise mudstone-dominated sequence. So, as you said, this is different to most PTM sections. But similar increased siliciclastic inputs into the deep marine basins during the PTM also exists in northern Spain. In terrestrial systems, for example, in the Bighorn Basin, there's evidence for the modification of flow valve system morphology and stream power in response to increased precipitation and sediment loads.
So Shell drilled that well that you studied in 2004. And they drilled through most of the stratigraphy without recovering cores. But exactly at the PTM, they recovered more than 100 meters of core. That's not a coincidence, right?
Yes, the sand information in the Aaron field is a sand-dominated hydrocarbon reservoir. So they were most interested in recovering cores through the turbidite sandstones in this formation. And from my research, we now know that the occurrence of these sandstones was directly linked to the PTM event.
So Shell didn't know that they would core the PTM when they did it?
Yes, I think so.
In your paper, you start from the hypothesis that turbidite deposition may be sensitive to astronomical forcing in greenhouse climates. So to test that hypothesis, you carry out time series analysis on the turbidite sequence. But that is not as easy as it may sound. First, because turbidites are deposited instantaneously on geologic timescales, so their thickness is not really a good proxy for geological time. And second, because your turbidite series is a point event series, not a nice sinusoidal series. So you can't really apply Fourier transform-based techniques for time series analysis to your record.
Correct. The variable thickness of sandstones in the succession bias these depths. and the turbidite sandstone beds are deposited geologically instantaneous, as you said. So we determine the depth of each sandstone bed in a succession after removal of sandstone thicknesses. This gives us a point event series, kind of like a calendar of sandstone deposition events. As you said, our turbidite series is not suitable for Fourier transform. In this case, circular spectrum analysis can be used to analyze periodicity in unevenly spaced discrete binary data like ours. The principle is fairly simple. Imagine that if you wrap the depth or time series around the circle, if there is a periodicity, then the data points will cluster around one point on the circumferences of the circle of that length. We also apply two other techniques as well as Monte Carlo modeling of random data to back up the results we got with circular spectrum analysis. All of these methods suggest that there's a 5-meter periodicity in the stacking pattern of our turbidites, and the confidence level is higher than 95% in all these analyses.
Yeah, that's really a nice workaround, avoiding Fourier-based techniques and working with these event series. Very well done. Of course, you have more proxies than just the occurrence of turbidites. You also measured the carbon isotope composition of organic matter, and you looked at the abundance of certain dinoflagellate cysts. Those proxies allowed you to really pinpoint the onset, the body, and the recovery of the PTM. And what struck me when reading the paper is that the dinocysts, they peak several meters below the onset of the delta 13C excursion, so the carbon isotope excursion. Does that mean that global warming began prior to carbon release?
Yes, the onset of the CIE may slightly lag the rise in the abundance of Apectodinium species. This suggests that the environment favorable for Apectodinium, like sea surface temperatures and salinity, may have begun to change before the CIE. Juries also found that the onset of the CIE lagged the onset of the Apectodinium achim in a well, which is 100,000 kilometers away, as well as in the North Atlantic and the Southwest Pacific Oceans. These findings suggest that environment changes had indeed begun prior to the carbon release.
Whoa, that is pretty interesting. Okay, let's now go back to the turbidites away from the carbon isotopes. Your data clearly shows that the frequency of turbidites goes up significantly during the PTM. You have more than 200 turbidites during the PTM, but they are largely absent before and after the event. If we think about possible triggers, tectonic uplift comes into focus, as well as sea level change and climate change. What is your view on this? Why do we observe this sudden increase in turbidite frequency during the PTM?
Certainly, we can expect tectonics to have played a key role in the development of turbidite systems in the North Sea. Nevertheless, it's striking that in our well, specifically, we only see turbidites within the PTM. The total duration of the PTM has been estimated to be around 200,000 years. This is below the timescale over which a purely uplift-induced increase in sediment supply would likely operate. Regarding a sea level trigger, global sea level rose during the PTM, likely increasing shelf sediment stability. So this would not be conducive to turbidite deposition. Given these considerations, and the coincidence of turbidite sandstones entirely within the peak of an extreme hypothermal event, we attribute the sudden appearance of the turbidites in the succession to large-scale climate warming and the consequent amplifying effect that this had on regional hydrology and sediment supply. This idea is also supported by some recent work by Bailey that suggests increase in sediment supply alone can trigger turbidity currents.
So you are saying that the PTM turbidites in the studied core are triggered by climate change. That, of course, brings us to your astronomical interpretation. You already mentioned that you found a 5-meter rhythm in the stacking pattern of the turbidites with more than 95% confidence. Does that translate into one of the Milankovitch parameters?
Yes, as I mentioned, previous work had suggested a total duration of 200,000 years for the CIE. More recent timescale constraint based on a new astronomical solution from ZB and Lawrence suggests that the duration from the start of the onset of the CIE to the end of the most abrupt part of the recovery interval was 170,000 years. In our work, we recognize 8.3 cycles over a similar stratigraphic interval, encompassing part of the onset and all of the body of the CIE in the chord interval. This supports the likelihood that the 5-meter cycles in our record are 21,000 years astronomical precession cycles.
And your interpretation is backed up with climate modeling, right? You mentioned in the paper the effect of more water vapor in the atmosphere during the thermal maximum and atmospheric rivers building up over the Atlantic Ocean in the direction of the European coast, causing more frequent extreme precipitation events.
Yes, and elevated greenhouse gas conditions. The relative positioning of the atmospheric rivers appear to be sensitive to orbital configuration, which might explain the increased intensity of sediment erosion, thus affecting marine sediment delivery. Certainly, we know that hydrological systems were strongly affected by the PTM, and large increases in sediment supply are seen in other places too.
It's time for the number of the month. Your last answer about atmospheric rivers and extreme precipitation events brings us back to the discussion whether or not the PTM is a good analog for anthropogenic global warming. Indeed, the extreme floods in Belgium and in Western Germany last summer are still very fresh in my memory, and we have to know whether or not such events are going to hit Europe more frequently in our warming climate. So I did a quick Google Scholar search looking for articles published in 2022 that mentioned the PTM. There were no less than 53 papers. That's more than one paper per day. So the number of this month is 53, and it illustrates what a hot topic the PTM currently is in geosciences. What is your view on the discussion whether or not the PTM is a useful analog for anthropogenic global warming? More than one paper per day, does that reflect our societal duty as a paleoclimate research community, or might it be a little bit exaggerated?
I think the PTM is useful, but not perfect analog for current global warming. The two timescales are, of course, quite different. Identifying potential triggers and feedbacks will aid with exploring the climate sensitivity and setting the boundary conditions for hydrothermals in models. In our study, we uncover the thickest record of the PTM yet documented, so we have a lot more details on the temporal evolution of the event. For example, our record shows the possible pre-onset environmental changes, whereas the lagged response of the coarse sediment system to environmental change. Overall, I think the effects that the PTM had on hydrological cycle can teach us a lot about how the climate system could change in the future to continue carbon release.
Okay, back to the science now. I want to know how exactly you measured the carbon isotope composition of organic carbon preserved in those sediments, because those sediments were in contact with hydrocarbons. Otherwise, shell wouldn't be there, right? And they were in contact with drilling mud. How did you make sure that you were not measuring a contaminated signal?
Yes, as noted before, the sand formation is a sand-dominated hydrocarbon reservoir. So migrated hydrocarbons and drilling mud may pose a potential challenge for retrieving the original TOC and the delta 13C of the rocks. To avoid the contaminated signal, or on-ground wet cutting samples were washed 3 times with DCM to remove soluble superficial organic matter and drilling mud components. In order to assess whether DCM washing could have significantly affected the delta 13C and the TOC values, Subsamples of lighting of the core samples were also washed with DCM to directly compare data between washed and unwashed samples. And the result is that to remove potential migrated hydrocarbons and drilling mud contamination with DCM ocean are unlikely to significantly affect our .13C data and the reconstruction of the PTM CIE.
All right, so you are pretty confident you obtained a primary carbon isotope signal. That's good news because it is the most expanded PTM section known to date. How is your carbon isotope excursion in the North Sea comparing to other reference curves like Sumaya or Walvis Ridge or the Bighorn Basin?
The pattern of the CIE in this study is unlike that of Walvis Ridge. In pelagic sections, the rapidity of the onset is frequently enhanced by carbonate dissolution. However, the box-shaped CIE recovered in our well is similar to other relatively high sedimentation rate sites, such as those recorded from shallow water and terrestrial sections at Tundra, Claret, and the Bighorn Basin. The CIE magnitude of our record is 3.36 per mil, which is bigger than the CIE of typical pelagic sections, but smaller than typical terrestrial sections.
Thank you, Simin. I really enjoyed talking to you about the PTM. What I really liked about Simin's work is that it's a textbook example of how exciting paleoclimate stories can also be told from siliciclastic sequences. It might be a little bit more challenging to get a carbon isotope curve, and also in terms of time series analysis, non-Fourier-based methods come into focus. But those are relatively small efforts if one considers the amount of truly new information that Simin was able to extract from the offshore well she studied in the North Sea. Thank you for listening and see you next time.